Hello, welcome. And today we'll be looking at Fourier series. We're going to be looking at what is Fourier series, what really is Fourier series. All right, I'm going to be introducing you and giving you key information that you need to know about Fourier series that will help you in the long run in your journey of Fourier series in this video. Now, Fourier series are used for periodic signals to expand them in terms of their harmonic, which are sinusoidal and orthogonal. The concept of Fourier series was first developed by Fourier series. So it says what Fourier series are used for periodic signal to expand them in terms of their harmonic, which are sinusoidal or orthogonal, and it was first developed by Joseph Fourier. Now, we have types of signals. We have two types of signals, all right? We have two types of signals. We have the periodic signals and the non-periodic signals. So, what are the periodic signals? The periodic signals is a signal that repeats itself after a particular interval of time. So, for every interval of time, it is repeating itself. Because don't forget, period. What's period? Period means one complete cycle. Period is one complete cycle. One complete cycle. So when we're talking about period is one complete cycle. Alright? So a periodic signal is a signal that repeats itself. It keeps repeating itself. It becomes a pattern that you keep seeing over and over again over a particular interval of time. Alright? Now, take a look at this diagram. Take a look at this diagram and see what I'm saying. Now, this is our y-axis, which is also our f of x axis. This is our x-axis. Now, look at. So you see, it starts from 0, comes here, and then stops here. That's a full cycle. That's a full period. Now, it starts again from this point and goes again. Now, if you notice, it starts from here, comes here, and stops here. This, from here to here, is pi. Then from here to here is 2 pi. It means that the period of this periodic signal or function is 2 pi, because it takes it 2 pi units to complete a whole full cycle. And if you notice, it is periodic because it continues to repeat itself at the same interval of time. Alright, so I can go further to express this, that f of x is going to be equal to f of x plus t is equal to f of x plus 2t, and so on and so forth from what I have here. And what is t? T is 2 pi. T is the period. That's how long it takes it to complete a full cycle, or how long it takes to make a complete cycle. So, of course, I said t is the period of the function. So, meaning I can also write this apart from expressing the function of the period like this. Apart from expressing the function of the period like this, I can also express it as this. I can also say f of x is equal to f of x plus 2 pi is equal to f of x plus 4 pi, and so on and so forth. It keeps going like that because one complete cycle is a period, and the period for this periodic signal here is what? 2 pi. Alright? So now let's go further. Now let's look at non-periodic signals. These are signals that are not repetitive. They occur haphazardly. Alright? They occur haphazardly, meaning anyhow. Alright? They just occur haphazardly, anyhow. They don't have a constant movement, alright? Or a constant signal, or a constant pattern. So they occur haphazardly and are extremely difficult to analyze. Now take a look at this diagram. You see, it starts from here and then it moves like this. And before you know, it comes here, and before you know, it moves down here. So it is not constant. It does not have a regular pattern. And many of the times are very, very difficult to analyze. So this is a periodic function. And diagrammatically, this is an expression of the periodic function. And then this is a non-periodic function or signal. And diagrammatically, this is the expression. Alright? Let's go further. Now, let's look at the Fourier equation. Let's look at what the Fourier equation. Now, f of x The Fourier equation is what? F of x, right, is this, that f of x is equal to a naught over 2 plus summation n from n is equal to 1 to infinity an cos nx plus summation n from n is equal to 1 to infinity bn sin x. All right, where a naught, an, and bn are called the Fourier coefficients. All right, so Fourier equation can further be expressed as f of x is equal to a naught over 2 plus a1 cos x plus a2 cos 2x plus a3 cos 3x and so on and so forth, plus b1 sin x plus b2 sin 2x plus b3 sin 3x plus so on and so forth. Now n is equal to the number of harmonics. This n you are seeing here is equal to the number of harmonics. That means how many times. So is from n is equal to 1, that's first harmonic, n is equal to 2, second harmonic, n is equal to 3, third harmonic, n is equal to 4, fourth harmonics. All right, fourth harmonics. So now f of x is, of course, is the DC component. That's the direct component value. Now this f of x here can also be written like this. You can see summation and summation from n is equal to 1 to infinity is common here and here. So I can just I can decide to factorize it out and still write this like this. Now let's go further to look at more concepts on Fourier series that is going to help us in our journey in Fourier series. So now our Fourier coefficients, now these are their formulas. We have a naught, we have an, and we have bn. Now a naught has the formula of 1 over pi from integral of 0 to 2 pi of f of x dx. An has the formula of 1 over pi integral from 0 to 2 pi of f of x cos nx dx. And then bn has the formula of 0 to 2 pi f of x sin x, 1 over pi integral from 0 to 2 pi of f of x sin nx dx. Now, he said if f of x is even, that is, of course, you know, when a function is even, f of minus x is going to be the same thing as what? F of x. So when you have, when the f of x is even, when the function is even, only sine terms appear. That means when you're finding your Fourier series, only the sine terms will appear. All right. So this is how it's going to be. So the sine terms will disappear, only the cosine terms will remain. Now, if your f of x is odd, that is, if f of minus x is equal to minus f of x, that's, of course, you know, this is when the function is odd. Only sine terms appear, cosine terms will vanish. Only sine terms will appear, the cosine terms will vanish. That's what you can see from here. Now, some students have really asked me, what does it really mean for a function to be odd and for a function to be even? What does it really mean? It's very simple. Just watch this. Now, try on your calculator, try pressing cos 60. That's cos 60 degree. And also try pressing cos minus 60 degree. Also, try pressing sine 30 degree. And also try pressing sine minus 30 degree. Now, cos 60 degree is going to be what? If you press it on your calculator, you notice that cos 60 degree is what? Is going to be what? 1 over 2 or 0.5. If you press cos minus 60, you are going to also have 1 over 2. But if you notice something, if you press sine 30, you have 1 over 2. But if you press sine minus 30, you are going to have minus 1 over 2. So this is a pure example of an even function. This is a pure example of an odd function. Because cos 60, that's f of x, is the same thing as f of minus x. So if you press cos 60 and you press minus cos 60, you still get the same thing. But if you press here, if you press sine 30 and you press minus sine 30, you will not get the same thing. So that's why sine is an odd function and cos is an even function. Please, I hope you understand that now. So that's what it means for a function to be odd and even. That when it's even, f of minus x, the negative of your f of minus x is still the same thing as f of x. But when it's odd, that's what? F of minus x is equal to minus. They are not going to be the same thing. This is not equivalent. So they are not. So that is what it means for a function to be even and a function to be odd. Now let's go ahead and look at some other things that we need to know that will help us in our journey of Fourier series, other important formulas, integrals that we need to know that will help us in our journey of Fourier series. But before we go further to look at those other important formulas or things we need to take note of, let's quickly look at symmetric interval. Now, symmetrical interval is equal to interval that goes from minus L to plus L. So, meaning it's going from negative to positive. Just like saying minus 1 to plus 1. Alright? Why does symmetry matter? Why does symmetry matter? It says because when the interval is symmetric, for an odd function, of course, you know, for an odd function, f of minus x is equal to minus f of x. Integrate to 0 over that integral. They integrate to 0. So, for instance, if I have an integral, all right, if I have an integral of what? Minus pi to pi. This is symmetric because it is minus pi to pi. Just like we said, minus L to plus L. So if the function is what? If the function is odd, that's if f of x is odd, all right, it will integrate to 0. All right, it will integrate to 0. But for even functions, when you have f of minus x is equal to f of s, it keeps the integral. The integral will be kept. That means if you are integrating from an interval of minus pi to pi, and your f of x is even, your integral will be kept. That means your integral is going to be kept. All right. But if it's odd, your integral tends to 0. That's what it's trying to say. Now note, for a period of 2 pi, a symmetric interval is minus pi to pi, just like I've said here. So, for instance, if we have an interval of minus pi to pi, it means that the period is 2 pi. Also, you see that for a period of 6, a symmetric interval is what? Minus 3 to 3. So, meaning that if I have if I have an interval of minus 2 to 2, it means that the period is what? 4. All right, the period is going to be what? The period is going to be 4. Please, I hope you understand this. The period is going to be 4. So that's how it goes. Now, let's go ahead to finally look at those other things that we need to know that will help us in our journey in Fourier series. These are the useful integrals and formulas that we need. Now, the first one says what? Integral from 0 to 2 pi of sine nx dx is equal to 0. So when you see this, you do not need to waste your time to start integrating. You just know that the answer is going to be 0. That's when you're having an integral from 0 to 2 pi on that condition. Also, for this one too, integral from 0 to 2 pi of cos nx dx is equal to 0. So when you see this, you don't need to waste your time and start integrating. You just know that this is 0. And then for this too, integral from 0 to 2 pi of sine square nx dx is going to be equal to pi. So this one is going to be equal to pi, and the same for cos square nx dx is going to be equal to pi. And then for sine nx sine mx, that means what this is trying to say is that the coefficient here is going to be different from the coefficient here. So this n in this case can be 2, this can be 3 or 5 or any other number. But if you integrate this, and especially when they have this interval of integration, you're going to have what? 0. Especially when they have this interval from 0 to 2 pi, you're going to have 0. The same for this, and then for this also, and also for this. And also note that sine pi n, which can also be written as sine n pi. You know, some people write it as sine n pi, some people write it as sine pi n, is equal to 0. All right? Sine pi n is equal to 0. Why cos pi n is equal to minus 1 into bracket minus 1 to the power of n. Take note of this. And then cos 2n pi is 1. Sine 2n pi is 0. All right? Please take note of that. Now, when the function is even, minus 1 to the power of n is going to be equal to 1. Of course, when it is what? When it is odd, is going to, when you are having odd numbers, when you put your odd numbers here, you're going to be getting minus 1. So take note of that. So these are some of the most important formulas that will help us in our journey of Fourier series. Make sure you like this video, share this video, and hit the subscribe button so when I upload more videos like this, you get notified. And I'll be uploading more videos on Fourier series. I'll be solving a lot of questions, and I'll also be making massive videos back to back on Fourier series. Make sure you stay tuned All right, make sure you check the playlist to see more videos on Fourier series so you could understand it better and so you could achieve what you want. Don't forget, you learn here, you excel, and you achieve.